Drop a pile of needles on a striped floor, and the mess will tell you pay. Watch. These needles are landing completely at random. Some cross a blue line, so they flash yellow. We count those, divide by the total, do one tiny bit of arithmetic, and there it is. 314. No circles, no circumference. Just sticks making a frankly irresponsible mess on the floor. And yes, this is a real way to estimate pi. You can do it at home with toothpicks, though I recommend telling everyone before you start throwing them around. Here are 10,000 simulated drops. Keep your eye on the number in the corner. At first it panics, 3.7, 2.8, 3.3. Then, as more needles land, it settles toward pi like it knew where it was going the whole time. That should feel suspicious. Pi belongs to circles, supposedly. Our floor contains parallel straight lines, and each needle is straight too. So where exactly is the circle hiding? I got hung up on the counting formula the first time and completely missed the physical trick. The secret begins with one needle, one nearby line, and a question that seems almost too small to matter. What decides whether that needle crosses? A needle crosses for a very ordinary reason. Its center lands close enough to a line. The annoying part is that close enough changes when the needle turns. Put the needle nearly vertical against these vertical floor lines. Its center can sit fairly far away, and one end still reaches across. Turn it nearly parallel to the lines, and now the center has to land absurdly close. So every drop really chooses two random numbers. First, the distance from the needle's center to the nearest line. Second, the needle's angle. Position and angle. That's the entire experiment hiding under the pile. Let's make the spacing between floor lines equal to the needle's length. Call both of them 1 unit for now. The center's distance to its nearest line can range from 0, directly on a line, up to 1/2, exactly midway between two lines. The angle only needs to range from 0 to 90 degrees, because flipping or mirroring a needle changes nothing about whether it crosses. Now comes the useful move. Instead of dropping needles, we can drop dots into a rectangle. The horizontal coordinate records the angle. The vertical coordinate records the center's distance. Every possible needle landing becomes 1 point. Somewhere inside that rectangle is a region meaning crosses. If we can draw its boundary, the whole floor experiment turns into an area problem. The shape of that boundary is where pi sneaks in. That boundary comes from the needle's sideways reach. Watch the yellow needle rotate while its center stays fixed. What matters is the horizontal piece of half the needle because the floor lines are vertical. If the needle is perpendicular to the lines, that sideways reach is 1/2. If it is parallel, the reach is 0. Between those positions, the reach changes smoothly. Draw a right triangle using half the needle as the hypotenuse. The horizontal leg is 1/2 times the sine of the angle, depending on how we chose the angle. Honestly, sine versus cosine here is mostly a bookkeeping fight. Pick the angle from the line itself, and we get sine. So the needle crosses exactly when the center's distance d is less than 1/2 sine theta. That's our boundary. On the rectangle, draw the curve d equals 1/2 sine theta. Every dot below it represents a crossing because the center is close enough. Every dot above it is a miss. And suddenly the random needle pile has one screenshot-worthy picture, a rectangle of every possible landing, with a sign-shaped yellow region containing every crossing. The probability of crossing is simply the yellow area divided by the whole rectangle. We haven't calculated either one yet, but the circle has finally left fingerprints. Sine came from rotation, and rotation is circle geometry wearing work clothes. Now the question has sharpened. How does the area under this particular sine curve turn into a formula containing pi? The yellow area answers the experiment because our dots are uniformly scattered across this rectangle. Equal-sized patches are equally likely, so a region taking up 60% of the rectangle catches about 60% of many drops. Randomness is doing geometry for us, which is a deeply weird and useful arrangement. The whole rectangle has width pi over 2 and height 1/2. Its area is pi over 4. The yellow region has area equal to the integral from 0 to pi over 2 of 1/2 sin theta. That integral equals 1/2. If integrals are currently giving you the 1,000-yard stare, the only fact we need is this. The area undersigned from 0 to pi over 2 is 1. Scale the curve vertically by 1/2 and the area becomes 1/2. Now divide yellow area by total area. 1/2 divided by pi over 4 gives 2 over pi. That means about 63.7% of the needles should cross a line. Turn the formula around and pi equals 2 divided by the crossing fraction. If C needles cross out of n total drops, the fraction is C over n, so our estimate is 2n over C. That's the little arithmetic trick from the opening. But this raises a fair complaint. We used pi to label the angle rectangle, then proudly recovered pi at the end. Is this just pi laundering? To see why the experiment still works physically, we need to find the circle inside the average sideways reach. The pi in the answer comes from averaging a rotating segment, and there is a lovely way to see that without staring at the integral. Take the needle and pin one end down. Now sweep the other end through a half turn. Its tip traces a semicircle. During that sweep, look only at the needle's horizontal projection, the same sideways shadow that decides crossings. Near vertical, the shadow is large. Near horizontal, it shrinks. Averaging that shadow over every angle produces 2 over pi times the needle length. Why? Imagine unrolling the semicircle's arc into a straight strip. Its length is pi times the radius. Meanwhile, the total accumulated vertical or horizontal change over the sweep is tied to the diameter, 2 times the radius. The ratio of that straight displacement scale to the curved arc scale is 2 over pi. The calculus says the same thing more cleanly, but this picture is the source. A rotating needle carries a semicircle around invisibly because its endpoint could lie anywhere along that arc. The floor lines only measure the needle's shadow in one direction, so our crossing rate compares the straight length, the needle's effective average reach, against the spacing of the lines. Pi appears because the average projection of something rotating depends on the circumference of its possible directions. That answers the cheating complaint. You never need to know pi to perform the drops. Nature samples the angles, and the crossing count measures the average projection for you. Now we should test whether the promised formula survives actual small, ugly data. With 20 drops, this method is terrible. I want to show that plainly because clean simulations can make probability look way more obedient than it is. Here goes needle 1, cross, needle 2, miss. After 5 drops, our estimate says 5. After 8, it says 2.67. At one point, the estimate shoots off the chart because we have too few crossings. The needles are technically estimating pi in the same sense that my first pancake technically estimates a pancake. Give them time. At 20 drops, suppose 13 crossed. 2 times 20 divided by 13 gives about 3.08. Pretty decent, mostly by luck. Repeat the same 20 drop experiment and we might get 3.64 or 2.86. Nothing is broken. The true crossing probability is about 0.637, but random samples wobble around it. At 100 drops, the estimate still breathes noticeably. At 1,000, it starts looking respectable. At 10,000, the fluctuations narrow around 3.4159, though they never freeze completely. This is the law of large numbers doing its slow, unglamorous job. More drops make the observed crossing fraction settle toward the true probability, and then 2 divided by that fraction settles toward pi. There is a catch hiding in the speed. Each extra decimal place costs an unpleasant number of needles. So how many drops would we need before this stops being a party trick and becomes a serious measuring tool? The bad news is that random error shrinks roughly like 1 over the square root of the number of drops. 10 times as many needles does not buy 10 times the precision. It buys about the square root of 10, a little over 3 times the precision. To make the typical wobble 10 times smaller, you need around 100 times as many drops. One extra reliable decimal digit can cost about a 100-fold increase in effort. Probability is stingy like that. With 1,000,000 simulated needles, you might get a few solid digits of pi. A modern computer can calculate vastly more digits using algorithms designed for pi, so nobody should replace their calculator with a warehouse full of toothpicks. The point is stranger and, to me, better. A geometric probability experiment can encode a mathematical constant in a physical frequency. The estimate exists in the repeated event itself. We can also put error bars around it. Crossings behave roughly like coin flips with success, probability 2 over pi. The number of crosses fluctuates by an amount proportional to the square root of n. Feed that uncertainty through the formula 2 n over c, and you get a shrinking interval around pi. Watch the band, rather than only the twitchy estimate. The band tells us how much trust the experiment has earned. but so far we've chosen the one suspiciously perfect setup where needle length equals line spacing. Real needles and real floorboards rarely cooperate. What changes if the needle is shorter? A shorter needle keeps the same logic. Its reach simply scales down. Let the needle length be L and the distance between floor lines be D, with L no greater than D. The center can be anywhere from 0 to D over 2, away from its nearest line. The sideways reach of half the needle is L over 2 times sin theta, so the crossing region is still under a sine curve, now with height L over 2. Inside a rectangle with height D over 2, the curve's area is L over 2. The rectangle's area is pi d over 4. Divide them and the crossing probability becomes 2, L over pi d. Turn that around and pi is approximately 2ln, divided by dc. Longer needles cross more often. Wider line spacing makes crossings rarer. Both facts pass the common sense test, which is always comforting after a formula arrives wearing 4 letters. Here's a useful animation check. Double the line spacing and keep the needle fixed. The crossing fraction halves. Double the needle length while it still fits between adjacent lines, and the fraction doubles. Pi sits in the conversion between random angle and average sideways projection. This version is the one you'd use at home. Measure your toothpicks, measure the gap between parallel lines, drop them, and count. There is one rule we slipped in quietly. L must be no greater than D. If the needle becomes longer than the spacing, it can cross more than one line. Then our tidy yellow region runs into the ceiling of the sample rectangle, and the formula changes shape. Once L exceeds D, some angles make the needle's sideways reach larger than half the line spacing. At those angles, crossing is guaranteed no matter where the center lands. On our rectangle, the sine curve rises above the ceiling, but probability cannot rise above the ceiling with it. We clip the region. The yellow shape now has a flat-topped middle and curved edges. That tiny geometric change produces a much uglier formula involving an inverse sine and a square root. I won't dump it on the screen like a bag of spare parts. The picture already tells us what matters. Short needles have one clean chance to reach the nearest line. Long needles can cross at least one line across a whole band of angles, and very long ones may cross several lines. We must also decide what event we're counting. Did the needle cross any line? How many lines did it cross? Those are different random variables. Here is the fun rescue. If we count the total number of intersections, instead of merely yes or no, the expected count grows cleanly with needle length again. A needle twice as long has twice the expected number of line crossings, even when it spans several gaps. Linearity of expectations saves the day without asking whether different crossings influence each other. That phrase sounds like a legal clause, but the idea is simple. Count each possible line crossing separately, then add their averages. This broader version points toward a much bigger principle. Random lines can measure the lengths and perimeters of shapes that are far more interesting than needles. A curved shape can be treated as lots of tiny needle pieces. Take this squiggle and break it into short segments. Each segment has its own angle, and under random placement and rotation, each one contributes an expected number of crossings proportional to its length. Add all those expected crossings and you get something proportional to the total length of the squiggle. The pieces may cross the same floor line, bunch together, or behave dependently. Linearity of expectation genuinely does not care. It is the chillest theorem in probability. Now close the squiggle into a convex shape. A randomly placed line that hits the shape usually enters and leaves, giving 2 boundary intersections. Counting intersections, therefore, connects the shape's perimeter to how often random lines hit it. This family of ideas belongs to integral geometry. You measure geometric quantities by averaging intersections over positions and directions. Buffon's needle is the pocket-sized version. Here is the pause-worthy frame. On the left, a straight needle with length L. In the middle, a curved boundary chopped into tiny colored segments. On the right, a cloud of parallel test lines. Beneath all three, cites the same statement. Average intersections measure length. Pi enters through averaging all orientations. The method can estimate the perimeter of shapes without tracing their boundary in the usual way. It can even help analyze fiber networks and microscopic structures. Before we get too grand, though, our home experiment has several boring ways to lie to us, and one of them is hiding in how people throw If your needles prefer an angle, the formula can fail. People are impressively bad random number generators, especially when wrists are involved. A gentle sideways toss tends to align needles. Dropping them in a clump creates collisions and overlapping pieces that are hard to count. Letting needles bounce off a wall biases their positions. Using floor lines with uneven spacing changes the sample space. And if your toothpick length is close to the line spacing, a tiny measurement error feeds directly into the pi estimate. I got an embarrassingly good result once because I had counted a needle, touching a thick painted line as a crossing whenever it suited me. That is called experimental technique. If you're trying to be fired, we need rules before the drops. Use thin parallel lines with measured center to center spacing. Keep the needles shorter than that spacing. Drop from enough height that their orientation spread out while avoiding a gale or a ceiling fan. Decide whether touching counts, then apply that rule consistently. Borderline cases have probability essentially zero in ideal geometry, though physical needles have width because reality enjoys paperwork. Photographing each batch before counting helps. Better yet, automate the geometry in a simulation and use the physical version as a sanity check. We can also diagnose angle bias. Make a histogram of landed orientations. A truly uniform orientation distribution should look roughly flat from 0 to 90 degrees. If one direction bulges, the needles are voting for an angle, and the pi estimate inherits that bias. Now let's design a version that a classroom could actually run without spending the afternoon arguing over one toothpick. Here is a workable setup. Draw parallel lines 10 centimeters apart on a large sheet. Use sticks 5 centimeters long, so L over D is 1/2. That makes the expected crossing probability 1 over P, about 31.8%. Nice and countable. Give each person 10 sticks and have everyone drop them one at a time over the center of the sheet. Ignore any stick landing partly outside the usable area because edges introduce a different kind of bias. After each round, record total valid drops N and total crossings C, with L equal to 5 and D equal to 10. The general formula 2L N over DC simplifies to N over C. So if 318 out of 1,000 sticks cross, your estimate is 1,000 divided by 318, about 3.145. That's a satisfying result, although another group may land at 308 and deserve the same grade. Plot the running estimate after every batch. Early points will look possessed. Later points should gather around pi. Then pool data across groups. One classroom can generate thousands of drops surprisingly quickly, provided someone is assigned to prevent toothpick sword fights. The pooled estimate usually improves because the sample gets larger, assuming every group used the same dimensions and rules. This is also a sneaky lesson about replication. Individual runs disagree. Combined evidence stabilizes. Yet, even with perfect procedure, a weird run remains possible. Randomness makes promises about long-run patterns, never about behaving nicely for us today. That leaves one final puzzle. Could we estimate pi with a completely different random object and still be doing the same underlying trick? Yes. Throw random points into a square containing a circle, and the fraction landing inside estimates pi over 4. Choose random whole numbers and count how often they share no common factor, and another probability reveals pi squared. Let a particle wander randomly, measure certain return patterns, and pi appears again. These experiments look unrelated, but they share a habit. Build a probability whose geometric or analytic size contains pi, then estimate that probability by counting random events. Buffon's version feels especially magical because the raw materials are so aggressively straight. Parallel lines, straight needles, a yes or no crossing. The curve enters through orientation, through the invisible semicircle swept by a rotating endpoint. Keep your eye on one final needle. As it turns, its sideways shadow grows and shrinks. As it drops, the floor asks whether that shadow reaches a line. Repeat the question enough times and the answers average over every direction. That average contains the ratio between a diameter and a circumference, 2 over pi, so the messy pile on the floor was measuring a circle all along, one projection at a time. I still find one part unsettling. The needles never coordinate. They never correct an earlier mistake, and none of them knows the target. The only thing guiding the estimate is that every orientation gets its fair share eventually, which means the real machine here is randomness itself. And here's the loose thread that bugs me. How much geometry could we measure if we stopped at drawing rulers on shapes and just kept throwing things at them?